Okay, last unit on this intermediate course. Man, just 4 more after this one. As a foundation of this, we're going to talk a little bit about measurement and the terminology. First thing you have to know is sensitivity. What it is, you want your gauge to be able to detect differences in the measurement. Rule of thumb, about 1/10 of the tolerance or the process spread, whichever is smaller. So for instance, if you got something's got a 1-inch tolerance, you want it to be 1/10 of an inch on your gauge. Reproducibility, the ability to reproduce a measurement. So we take something, you measure it, you want to get the same results over and over again, both by the same operator and hopefully by another operator. This affects both accuracy and precision. Accuracy being a lack of bias. So when you see a gauge that calls out, 0.325 inches, the piece you're measuring should be 3.25. So you don't want the gauge reading 3.28 or something like that. You want it to be reading whatever the true value is. And precision, you lay that out there, you want to lay 0.325, 0.325. You'd like to get the same reading every time. And again, by the same operator. Anytime you talk about measurement terminology, you always see this bullseye. And if you look at the upper left-hand corner, you got low accuracy, low precision. It means those bullets are just spread out everywhere, right? You don't know how to do it. And then upper right hand, you got low accuracy, high precision. This means you got a lot of bullets hitting in the same spot. They're just not hitting in the right spot. And if you look at the lower left corner, you see high accuracy, low precision. It's bouncing all around the bullseye, but it's not very tight. And you can make up for this thing. Think of the central limit theorem here, how we might be able to use this. And finally, what you hope to do is get a high accuracy, high precision. If you have that, you take one shot with a gauge and you got it done. Some more measurement terminology. Bias, that's the difference between the output of the measurement and what the true value is of the actual thing you're measuring. Linearity, this happens a lot, especially with strain gauges and things. If you get outside the range of the gauge, you start getting distortion. It's actually not linear. It's basically those follow a parabola or something. Percent agreement, how well the gauge agrees with the reference value. Think gauge blocks here. So this is the basis for the calibration. And precision and tolerance, this is the ratio between the measurement error and the tolerance. Again, you want to be able to get down to 1/10 of what the tolerance is and gauge it accurately. Some different types of way of analyzing your measurement. First one is precision to tolerance ratio. And what you do is you take readings of a certain part and measure how much that varies and gets your standard deviation. So you want to take 6 times that variation and divide it by your tolerance. If you got less than 1, you've got some issues here. Or more than 1, you've got some issues. I'm sorry, more than 1. Precision to total variation of the ratio. This is the same way to figure out the standard deviation of the error term in your gauge. But the variation, that actually comes from your process part. That's that normal curve, the standard deviation we've calculated. And finally, if you can, do a measurement systems analysis or a NOVA system. ASQ.org's got a nice little spreadsheet you can use. Minitab does a good job with this. It's probably the only time y'all mention Minitab favorably. Measurement system analysis. We'll have some videos on that. Process capability. There are 3 steps to this thing. First, got to plan what kind of data you're going to collect the data, and then analyze it. If you've been doing it right, you should already have some data out there. Okay, now we're just going to analyze it. The objective is to establish a state of control over the process. In other words, get it so all your variation is just random variation, and then you maintain that so it's just random variation. It has to be random. If it's not random variation, we can't analyze it using our Gaussian curves and our formulas. Now, one of the ways we're going to measure how good our process is compared to the specification. We do that with the Process Capability Index, or CP. And what you do is you take the standard deviation of the process, and this is after getting rid of all the outliers, the non-random variation, and calculate 6 sigma. In this case, my standard deviation is 5. So 6 times 5 is 30. My specification interval is the upper spec minus the lower spec, or 160 minus 100, or 60. And CP is just basically upper spec minus lower spec, which is 60, divided by my 6 sigma, and that gives me 2. So this would have a CP of 2.00. And what does that do for us? I'll leave that as an exercise, but that's pretty good. If we got less than 1, we got issues. That means we're making defective parts. They've done studies over the years, many studies, and they found that process will drift. And usually they'll drift about 1.5 standard deviations back and forth. So you got to follow these things with the drift. And averages and spread depend on the number of units and measures and duration of the measurements. So the longer you can measure it, the more data you have, of course, the better. For limited runs, with very few, what we do is we measure the first piece, if that's the spec, and the last piece, if that's the spec, we just assume the others are still in spec. That's for very small units. Attribute capability is possible to do this, but you got to take a lot of data because you're using proportions or the rate of non-conforming pieces. So this is like first pass yield, ppm, etc. So what you got is discrete data, go no go, that type of thing, and you're trying to figure out the attribute. And so what you're going to do is measure it by proportions. It takes a lot of data,